Let's consider the motion of the particles now over that position, r of t, that we've been just described. So I guess just in terms of example, if we consider the point x squared plus y squared is equal to 1, or the Cartesian equation I should say, obviously if the particle was, say, to start at 1, 0 and travel anti-clockwise, taking 2 pi units of time to complete one circle, then its path could be represented as, okay, x equals cos t, y equals sin t. So don't forget, if I put t equal to 0, I'd have x is equal to 1, y is equal to 0, so there's my starting point, okay. And we're going to take 2 pi because that's the period of our graph. So if I put, say, t equal to pi on 2, so what's that, 1.5 seconds later, I'd have x is equal to 0 and y is equal to 1. So we start at the point 1, 0, and then 1.5 seconds later we're at the point 0, 1. So we're travelling in an anti-clockwise direction. So all those things match off, yeah? So come down a little bit further. So then r of t equals 2 cos of 2 pi t plus sine of 2 pi t j. Again, x equals a component, y equals component, so it's an x squared plus y squared is equal to 1. At t equal to 0, we are at 1, 0. We could check. In this case, the period of that graph is 1. So it's going to take 1 unit of time. So maybe if I put t equal to a quarter, so a quarter of a second later, I get cos of 2 pi on 4 plus sine 2 pi on 4. So again, that takes my position to the point 0, 1. So I'm travelling around in an anti-clockwise direction. So we could sort of put an, oops, we tend to put an arrow in the direction of motion, okay? And obviously the same thing in here for the next example there, okay? Only we've got a negative sign there, which means our particle starts at negative 1, 0. Again, if we pick, say, a quarter, my graph at sort of t equal to, I get negative cos 2 pi on 4, which is 0, sine of 2 pi on 4, which is 1, so it goes to the point 0, 1. So we start at negative 1, 0 and go to there. So obviously I'm travelling in a clockwise direction that time, okay? So let's have a look at some more practical applications of it all. So again, similar process, sketch the path of a particle where a position is blah, blah, blah. So again, we can sort of soon state x equals minus t, y equals a quarter of t squared. So substitute in, so we soon get y is equal to x squared on 4. All right, so there's my Cartesian equation. The domain, well, if x equals minus t, the range is from negative infinity to 0 because t is greater than or equal to 0. And if t is greater than or equal to 0, the range of a quarter t squared is going to be 0 to infinity. So there's my graph. Again, at 0, we start at the point 0, 0. And then if I put t equal to 1, say, I end up at the point, what's that, negative 1, a quarter. So then I end up a little bit further. So the arrows there indicate the direction of motion. All right. So there's my motion in 2 dimensions. 3 dimensions, obviously I've just got a third function z of t in the k component. So if we have a quick look, there's my cos t sine t plus 2. So again, if I want to try and describe that motion there, x equal to cos t, y equals sine t, z is equal to 2. Again, I get x squared plus y squared is equal to 1 in terms of variables. And I've got z is equal to 2 always. So really that's going to give me a circle along the plane z equal to 2. So I've got x squared plus y squared equal to 1 as a circle, 2 units above that plane at the z equal to 2 point. So maybe I've got across that plane there at z equal to 2. Direction of motion, again, if I put t equal to 0, I'm at the point 1, 0, 2. And then if I just pick a small amount of time later, say pi on 2 seconds later, I'm at the point 0, 1, 2. So I'm travelling in an anti-clockwise direction again. And so I put little arrows in my direction of motion. Okay, so I guess the meatier part of our particles and our multiple and our parameters and introducing time is to try to determine if our particles will cross path or actually collide. Okay, and so the key point there is if our particles collide, they'll be at the same point at the same time. If their paths cross, it just means at some stage their I and J components match off. Yeah. So let's consider the first of those scenarios, and that is a collision. All right. So if our particles collide, it means that the I components for these two particles here will equal. All right. So particles will be at the same point at the same time. So if we consider the I components, it means 2t minus 3 is equal to t plus 2. And the j components, t squared plus 10 is equal to 7t. If I solve one system of those, and I chose to solve for j first, we can see we get two possible scenarios. So what we're saying is at t equal to 2 and at t equal to 5. So what that tells us is at t equal to 2 and t equal to 5, the j components are at the same point. Okay. Now, if I check at t equal to 2, the I components are at different points, so they're not going to collide. But if I check t equal to 5, we see the I components are at the same point. So that means then at t equal to 5 seconds, the particles will both be at the same point and they'll collide. All right. So at that point, we probably should put that in then. So at t equal to 5, what do we get? We get 7i plus 35j. So that's my point of collision. All right. Now, let's consider where the paths cross. So the paths cross means that the I and j components will equal, but they might equal at different times. Yeah. So we still want to equate the I and j components, but for different times. So because we need that to be true for different times, I'm going to introduce a different time for my R2 particle. All right. Now the reason I do that, if I keep time as being the same, I'm only ever going to get the point where the I and j components are equal at the same time. Okay. So if we equate I and j components with the different times, I get my 2t minus 3 equals s plus 2, my t squared plus 7 equals 7s. So if I rearrange that top line, I'll get s equals 2t minus 5, substitute that in, and I get t is equal to 5 and 9. All right, so what that tells me is that at t equal to 5, particle 1 crosses particle 2. And at t equal to 9, particle 1 crosses particle 2. So if I substitute t equal to 5 into the s equation, I get s is also equal to 5, which is telling me that s equal to 5 is when particle 2 crosses particle 1, hence a collision, which is what we discovered in the previous bit of working out. But if I put t equal to 9, particle S, okay, S is equal to 13, which means when T is equal to 9, particle 1 crosses particle 2's path, but it's not until 13 seconds that particle 2 will cross the corresponding path in particle 1, so they'll miss. Hence, it's not a point of collision. So the relative coordinates or the respective coordinates that we're interested in, and we looked at that previously, they're both at the 5-second mark at 7i plus 35j. Particle 1 at the 9-second mark is at 15i plus 9j, but particle 2 doesn't get there until the 13-second mark at 15i plus 9j. So it's the 15i plus 9j is the point where the paths cross, as well as 7i and 35j, but they don't collide because they get there at different times. All right. Finally, the distance between points when the particles are at t equal to 1. So if I put t equal to 1, I get the 2 particle points, substituting into the equations. Distance between points, square root of y2 minus y1 squared plus x2 minus x1 squared, etc. Probably should extend that square root sign, just a fraction. 4 squared plus 4 squared is 32, which is 4 root 2. Off you go.